Hi everyone, welcome back to Calculus with Jackie and Shadow. Today we're going to be talking about what it means for function to be continuous, and we're defining continuity at a point and over an interval. So let's start with the definition of continuity. So with all the types of discontinuities we've talked about, there's ones where there's a jump, so the limit from the left doesn't equal the limit from the right. Spirit and the other eagle aren't getting together, so the limit doesn't exist. And there's ones where the target x value has an undefined y value. So Jackie and Shadow, from either side, they're going to the same place, but they can't quite get there. So for it to be discontinuity, it has to have a limit that doesn't exist or an undefined value. So that means for the function to be continuous at a point, the limit has to exist and the actual y value has to exist. And the y value also has to equal the value that it's approaching. Like you can't have a point that jumps up suddenly. So let's look at an example of continuity at a point. So we have this graph down here, and we want to know at which of these x values is the graph continuous. So we have -3, -1, 1, and 2. So let's first look at -3. At -3, we got an open circle, so it's a whole or removable discontinuity. It's undefined, so it's not going to be continuous there. It's not A. Now let's look at B, which is -1. At -1, there's a filled in circle, so it's defined, but there's this big jump. The limit from the left doesn't equal the limit from the right. And then what about at x equals 2? Well, at x equals 2, we got this one going off downwards with no bound. It's decreasing without bound. And this one's increasing without bounds. So they're going off to infinity. So that's definitely not continuous. And that leaves us with C, which is x equals 1. Now, x equals 1, limit from the left equals limit from the right. It's all nice and smooth and continuous. So that's our answer. It's 1. Now let's look at the second topic, which is continuity on an interval. So for a function to be continuous on the interval a to b, it has to follow the rules for continuity at a point in every point between a and b. So a good way to think about this is an eagle flying across the graph. It should be able to just fly across the graph normally, like no shadow realm, no teleporting, just a nice, smooth, normal flight. And let's try this practice problem. So we got the same graph as before, but this time we want to know on what intervals is the function continuous? Well, before x equals -3, it's looking nice and continuous. There's no open circles until you get to -3. So we can say that it's continuous for x is less than -3. And also, after 2, it's just going down like that. There's nothing else that's not continuous. So for x is greater than 2, it's continuous. And What we really want to do is we want to find intervals where we don't find any of the types of discontinuity. So that's going to be something like -3 to -1. We have discontinuities at -3 and -1, but in between them is just this nice curve that's continuous. Like if you think about it, an eagle could just fly smoothly along that curve without anything weird going on. And similarly, once you get past this discontinuity at -1, it's nice and continuous until you get to 2. So now let's try it with algebra. So it's asking us what intervals this function is continuous, and we got this really complicated looking equation right there, and we have to try to figure out where it's continuous. And remember, it's basically what parts of the graph an eagle could fly on, what parts have no discontinuity of any type. So this function, it looks really complicated, but the stuff going on in the numerator doesn't really matter because nothing going on in the numerator will make it undefined. The only thing that will make it undefined is a 0 in the denominator. It could also have a limit that doesn't exist if there's an absolute value, but I don't see an absolute value in this, so we're good with that. So I'll give you a second to think about how you might want to factor this. So you notice we have x cubed minus 5x squared minus x plus 5. We have a coefficient of 1 and 5 twice, so we can separate these out. And then we can actually multiply this out by an x squared. So now we can just factor it because this is a 1. So we have x squared minus 1, x minus 5. And then x squared minus 1, this becomes x plus 1 times x minus 1. And now we've factored the denominator, so we know the zeros. So the zeros are going to be at x equals -1, x equals 1, and x equals 5. And that leaves us with the intervals where it's continuous are just the intervals that don't include the points where it divides by 0. So that's going to be -infinity to -1, -1 to 1, and 1 to 5. Now, one more thing is if you're given a table, you can't really know if it's continuous or not. Like, if you don't have any other information, a table alone isn't enough to know if a function is continuous. Because if you have a table which plots values like this, you might think that it would just be a nice continuous function that goes right up in a straight line through all of them. But that's not necessarily true. There could be jumps in something like this function f of x, where it just goes up a little bit and then jumps, and this is definitely not continuous. So that's something you got to watch out for. But that's it for today, and see you again next time.